On the night of March 29th, 2026, nobody saw it happen. There was no explosion visible from the ground, no light show across the sky, no alert pushed to anyone's phone, no breaking news ticker running across the bottom of a television screen somewhere. Somewhere 350 miles above the surface of the Earth, in the cold and absolute silence of low Earth orbit, a satellite that had been quietly circling the planet every 96 minutes simply stopped existing in the way it was supposed to exist. It broke apart. Slowly at first, then faster, shedding pieces of itself into the void surrounding it. Within hours, a commercial radar network called Leo Labs had detected what they formally described as a fragment creation event. Tens of new objects where there had been one, each piece now moving independently at roughly 0 miles per hour, each piece now on its own trajectory, each piece now part of the problem rather than part of the solution. The satellite was called Starlink 34343. It had been in orbit for less than a year, and it was not the first, it was the second. The first had happened 3 months earlier, in December of 2025, and that one had quietly re-entered the atmosphere before most people even learned its name. But the second one, the March one, is sitting at a higher altitude, and at 560 kilometers above Earth, the forces that would naturally bring it down work much more slowly. Some of those fragments will be up there for years, circling, waiting, adding their tiny but real contribution to an environment that, if you actually look at the numbers behind it, has been telling us something important for a very long time. What is happening in the space above your head is not a crisis in the way that the word crisis usually implies, something sudden and dramatic with a clear beginning and a visible peak. It is something slower than that, and in some ways more consequential for that reason. It is the story of an environment that humanity filled faster than it understood the implications of filling, a commons that belongs to everyone and is therefore protected by no one in particular, a problem that the people who study it professionally have been describing with increasing urgency, while the rest of the world went about the business of using the products that depend on it. Your GPS navigation, your weather app, the internet service that reaches places where no cable has ever been laid, the financial systems that synchronize across continents using satellite timing signals, all of it resting on an orbital environment that is, in the words of the European Space Agency's own 2025 report, already approaching the edge of sustainability in certain altitude bands. This is the story of a satellite that shattered, but it is also the story of a theory proposed in 1978 by a NASA scientist that the space community spent decades treating as a distant theoretical concern, and that the data of the last several years has been quietly, methodically, and uncomfortably beginning to validate. It is the story of a cascade that, once it truly begins, has no natural stopping point, and it is the story of a window that is still open, still real, still representing a genuine opportunity to do something meaningful rather than simply document the problem after the fact. Stay with it. The numbers are specific, the timeline is real, and what is happening in the silent dark above you matters considerably more than the news cycle around it suggests. Part 1. The event itself was unremarkable in the way that very consequential things often are. On March 29th, 2026, a Sunday morning, SpaceX lost contact with Starlink satellite number 34343. The satellite was part of what SpaceX designates Group 17-1, launched from Vandenberg Space Force Base in California aboard a Falcon 9 rocket. It had joined a constellation already numbering more than 10,000 satellites, the Starlink network that SpaceX operates as a commercial broadband service reaching customers on every continent except Antarctica, a network serving more than 10 million subscribers at the time of the event. The satellite was orbiting at approximately 560 kilometers above Earth. At that altitude, the geometry of orbital mechanics produces a specific rhythm. Gravity pulls the object toward the planet, but the object is moving laterally fast enough that the surface keeps curving away beneath it at the same rate it falls toward it. The result is a continuous state of falling that never quite arrives. Starlink 34343 circled the planet once every 96 minutes, which means that in a single 24-hour period it completed approximately 15 full orbits of Earth, crossing every latitude between about 53 degrees north and 53 degrees south, passing over oceans and continents and cities and wilderness and the open Pacific, doing its small but real part in a constellation delivering broadband to 10 million subscribers. Then something went wrong inside it. The exact nature of the failure was not immediately disclosed by SpaceX. The company confirmed the anomaly the following day, March 30th, describing it as an anomaly on orbit resulting in loss of communications. What Leo Labs, the commercial tracking firm operating a global network of ground-based radars designed specifically to monitor objects in low Earth orbit, reported was more specific. Their instruments detected what they called a fragment creation event. Tens of new objects appeared in the vicinity of the satellite's last known position within hours of the anomaly. Leo Labs assessed that the fragmentation was likely caused by an internal energetic source, rather than a collision with existing space debris or another object. An internal energetic source, in the language of orbital mechanics, typically means something related to the satellite's propulsion system or its batteries, both of which store considerable energy in compact form and both of which have failure modes that can produce rapid and violent fragmentation. Michael Nichols, SpaceX's Vice President of Starlink Engineering, shared imagery of the event publicly. This was a notable act of transparency for a company that does not always volunteer operational details about anomalies in its constellation. The imagery confirmed what the radar networks had already detected. The satellite had shed material. The satellite was, for all practical purposes of mission operations, gone. SpaceX issued a statement that the debris posed no new risk to the International Space Station, its crew, or the upcoming launch of NASA's Artemis II crewed lunar mission, scheduled for April 1, 2026. Then, approximately 6 hours after confirming the anomaly, SpaceX launched another group of 29 Starlink satellites from the same launch site. Jonathan McDowell, an astrophysicist and satellite tracker formerly of the Harvard and Smithsonian Center for Astrophysics, and one of the most respected independent voices in the field of orbital mechanics, told Scientific American that he did not see how the risks could be zero. They are low, he said, because all the debris is expected to re-enter quickly. But I would like to hear more about why they assess the risk to be zero. And if these Starlinks have been breaking up due to an inherent design flaw, McDowell added, then the risks go up a lot. That last part is the sentence worth sitting with, because Starlink 34343 was not the model's first failure. It was the second. And the specific model involved, the V2 mini-optimized version of the Starlink satellite, has 3,532 copies currently in orbit. Understanding what that number means requires understanding what happened 3 months earlier and what it revealed about the situation. Those 3,532 satellites are now in together. The first fragmentation event in this sequence occurred on December 17, 2025. Starlink satellite number 35956, orbiting at a lower altitude of approximately 418 kilometers, experienced what was described as a propulsion tank venting event. The satellite dropped 4 kilometers in altitude almost immediately after the anomaly began, lost all communication with ground controllers, and began shedding a small number of trackable objects into the space around it. Leo Labs issued a report similar to the one they would issue 3 months later. An internal energetic source, a fragment creation event, a loss of communications. The resolution in that case was relatively clean, at least by the standards of the problem. Starlink 35,956 re-entered Earth's atmosphere on January 17, 2026, approximately a month after the anomaly, confirmed by the Aerospace Corporation. The debris was brief, low altitude, and self-correcting. The satellite's low orbital altitude meant that atmospheric drag worked on the fragments quickly, pulling them progressively lower until the thin upper atmosphere generated enough resistance to end their journey. Starlink 34,343 is not in the same situation. It was operating at 560 kilometers, which is within the constellation's standard 550 kilometer shell, but above the altitude where passive deorbit works on a timescale of months rather than years. During periods of reduced solar activity, the sun's output of high-energy radiation decreases, which in turn reduces the density of the upper atmosphere, even at relatively low altitudes, which in turn reduces the atmospheric drag that acts as the long-term garbage collector of low Earth orbit. At 560 kilometers during a solar minimum, an uncontrolled satellite or its fragments can persist in orbit for more than 4 years before atmospheric drag brings them down naturally. 4 years. in the most congested altitude band in the history of human spaceflight, among tens of thousands of other active and inactive objects. That is the duration of the problem created on the morning of March 29, 2026, and that is the context in which every subsequent piece of this story needs to be read. Part 2. What makes the March 29th fragmentation event harder to dismiss as an isolated technical anomaly as the company it keeps? In the months surrounding it, the orbital environment above Earth was generating a pattern of events that, taken individually, could each be explained as bad luck or normal engineering variants. Taken together, they describe something else. Start with the December 2025 Starlink failure. The two events are connected not just by their proximity in time, but by their shared model. Both Starlink 35,956 and Starlink 34,343 were V2 mini-optimized satellites. This is the latest generation of Starlink hardware, the version that SpaceX began deploying as part of its next phase constellation expansion. There are currently 3,532 satellites of this specific model in orbit. Two of them have experienced onboard failures resulting in fragmentation events within a 3-month window. Leo Labs, in its assessment of the March event, explicitly noted the similarity to the December event, writing that the two events illustrate the need for rapid characterization of anomalous events to enable clarity of the operating environment. The concern implicit in that language is the concern that McDowell made explicit. If these failures reflect a design pattern rather than independent random failures, then the population of 3,532 V2 mini-optimized satellites currently in orbit represents a risk that has not yet been fully characterized or disclosed. SpaceX stated it was working to determine the root cause and would rapidly implement corrective actions. Whether the corrective actions reach the 3,532 satellites already in orbit, how quickly, and what the failure rate for that population will be before the root cause is fully understood and addressed, those questions do not have public answers as of this telling. Now move 6 weeks back from the December Starlink event to January 30th, 2026. On that date, a Russian satellite called Lush, also known by the designation Olymp, and tracked by the catalogue number 40258, fragmented in what is called graveyard orbit. Graveyard orbit is the informal name for the high-altitude band, generally above 36,000 kilometers, where geostationary satellites are sent at the end of their operational lives to drift safely away from the active geostationary belt below. The rationale is straightforward. A dead satellite left in the active geostationary belt is a permanent collision hazard. Moved to a higher orbit, it drifts harmlessly, or that has always been the assumption. Jonathan McDowell told Space.com that the Luch fragmentation may have been caused by an external debris impact rather than an internal failure. This distinction matters considerably. Internal failures are engineering problems. A battery fails, a propellant tank vents, a component malfunctions. These events can be studied, root causes can be identified, design changes can be implemented. They're controllable in principle even when they're difficult in practice. A debris impact is a different category of event entirely. A debris impact means that the density of objects in the graveyard orbit environment has reached a level where even a retired satellite, drifting in a region specifically designated as the responsible place to put things you no longer need, is being struck by other material. It means the problem is not confined to the busy operational altitude bands. It means the debris environment is generating its own events independent of any ongoing human activity. If McDowell's assessment is accurate, the junk is finding the junk. The graveyard orbit fragmentation passed through the mainstream news cycle with almost no traction. There was no dramatic imagery. There was no immediate threat to the ISS or to any crew. The event was confirmed and catalogued and noted in specialist publications, and then largely set aside while the next item in the news cycle took its place. But in the community of people who study orbital debris professionally, an event like this carries a specific weight. It represents evidence that the orbital environment is not simply being filled by new activity, it is beginning to generate activity of its own. Lay those three events out in sequence. December 17th, 2025. Starlink 35,956 fragments internally at 418 kilometers. January 30th, 2026. Luch Olymp fragments in graveyard orbit, possibly from a debris impact. March 29th, 2026. Starlink 34,343, same model as December's failure, fragments internally at 560 kilometers. 3 events in 3.5 months, across different altitude regimes, involving different types of operators, with 2 different failure mechanisms. That sequence is not a random scattering of isolated bad luck, it is a trend. And understanding what that trend points toward requires understanding the physical environment in which all of these events are occurring, the actual density of objects in low Earth orbit right now, and what happens when that density crosses a specific threshold that a NASA scientist identified with considerable mathematical precision nearly 50 years ago. The numbers involved are worth sitting with because they are genuinely difficult to internalize at full scale. According to the European Space Agency's 2025 Space Environment Report, Earth's orbit currently contains approximately 1.2 million debris fragments, larger than 1 centimeter in diameter. There are also approximately 140 million fragments, larger than 1 millimeter. There are roughly 54,000 objects larger than 10 centimeters, of which about 43,500 are actively tracked by space surveillance networks. The rest, the ones between 1 centimeter and 10 centimeters, the ones between 1 millimeter and 1 centimeter, the hundreds of millions of fragments too small to track reliably from the ground, are known to exist statistically rather than individually. Scientists know they are there because the mathematics of collision events and fragmentation require them to be there. But no tracking system on Earth can see them directly. This creates a specific and genuinely uncomfortable gap in the picture. The objects that can be tracked and avoided represent a fraction of the objects that pose a collision risk. The objects that cannot be tracked, the centimeter-scale fragments moving at orbital velocity, are individually too small to destroy a large satellite on their own in most cases. But they are large enough to damage critical systems, large enough to initiate a tumble in a satellite that then loses attitude control, large enough to puncture a propellant tank in a way that produces exactly the kind of venting event that destroyed Starlink 35,956. An object 1 centimeter in diameter, travelling at orbital velocity, carries the kinetic energy of a hand grenade. That is not a comparison chosen for dramatic effect. It is the calculation produced by the mass and velocity of the object, and it comes from the ESA's own documentation of the debris environment. The problem with a debris environment you cannot fully see is that you cannot fully avoid it. Starlink's satellites performed 144,404 collision avoidance maneuvers in just the first 6 months of 2025, according to IEEE Spectrum. That is a collision warning being issued somewhere in the constellation every couple of minutes, around the clock, 7 days a week, for 6 months. The rate was 3 times higher than the rate during the previous 6-month period. Each maneuver consumes fuel. Each satellite that runs out of fuel before completing a controlled deorbit at the end of its operational life becomes another uncontrolled object in the most crowded altitude band in the history of spaceflight. The satellites doing useful work and the satellites that have stopped doing useful work are now sharing the same corridor. Part 3. To understand why a single satellite breaking apart matters at a scale beyond the satellite itself, beyond even the constellation it belongs to, you need to understand the physics of what happens to debris in low Earth orbit. Because the physics here does not work the way intuition suggests, and the gap between what feels like it should be true and what is actually true is precisely where the danger lives. Start with the most basic fact. Objects at orbital altitude do not simply fall when they stop working. Gravity at 560 kilometers above Earth is still approximately 83% as strong as it is on the surface. The reason satellites do not fall is not that gravity is absent. The reason is that they are moving sideways fast enough that the surface of the Earth keeps curving away beneath them at the same rate they fall toward it. This is what an orbit is, not an escape from gravity, a continuous, precisely calibrated falling that misses. When a satellite fragments, each piece inherits the velocity of the original object, approximately 17,000 miles per hour in the case of objects at the Starlink constellation's altitude, with a small additional velocity component applied by the energy of the fragmentation event itself. Each fragment is now on a slightly different trajectory. Over days and weeks and months, these trajectories diverge. A debris cloud that began as a tight cluster around a single point in space spreads into a diffuse shell of material, distributed across a range of altitudes and orbital inclinations, intersecting the paths of thousands of other objects. This spreading process is not a problem that resolves itself quickly at the altitudes where most of the world's active commercial satellites operate. At 400 kilometers, the altitude of the International Space Station, atmospheric drag is significant enough to bring uncontrolled debris down in a matter of months to a few years. At 550 to 600 kilometers, where the bulk of the Starlink constellation operates, and where dozens of other planned satellite constellations intend to deploy, the situation is more complicated. During periods of high solar activity, when the sun's output of ultraviolet and X-ray radiation is elevated, the upper atmosphere expands outward somewhat, increasing the density at higher altitudes and therefore increasing the drag on objects in that range. During solar minimum, the opposite occurs. The atmosphere contracts, drag decreases, and the amount of time an uncontrolled object persists at 550 kilometers before naturally deorbiting can stretch from months to years. A piece of debris the size of a marble, which is to say approximately 1 centimeter across, weighs almost nothing. But travelling at 17,000 miles per hour, the kinetic energy it carries is equivalent to a hand grenade. This is not a loose approximation. It is the result of applying the standard kinetic energy formula to the mass and velocity of the object, and the number it produces is what the European Space Agency, the world's most comprehensive institutional tracker of the debris environment, uses in its official documentation to convey the scale of the threat posed by small untraceable fragments. A piece 10 centimeters across, roughly the size of a softball, carries the kinetic energy of a small car bomb. ESA's 2025 Space Environment Report estimates there are approximately 54,000 objects of that size currently in Earth orbit. Of those, roughly 43,500 are actively tracked by space surveillance networks, meaning their positions are known well enough to issue collision avoidance warnings to satellite operators. The remaining roughly 10,000 objects at that size, plus all of the 1.2 million fragments between 1 and 10 centimeters, plus all of the 140 million fragments between 1 millimeter and 1 centimeter, are known to exist statistically, but cannot be tracked individually. Their positions at any given moment are unknown. Their future trajectories cannot be predicted. They cannot be avoided because no one knows where they are. This is the aspect of the orbital debris problem that tends to get lost in descriptions of the total number of tracked objects. When headlines report that tracking networks are following 36,500 pieces of space junk larger than 10 centimeters, the number sounds comprehensive. It creates the impression of a problem that is being monitored and therefore managed. What those headlines rarely convey is that the tracked population is not the threatening population. The threatening population is the millions of objects too small to track, large enough to cause serious damage, moving through the same volume of space as the satellites that provide GPS, weather forecasting, telecommunications, and increasingly, the internet backbone for rural and underserved communities across the developing world. In 2002, the crew of the Space Shuttle retrieved solar panels from the Hubble Space Telescope during a servicing mission. When engineers examined those panels on the ground, they found they were covered in small impact craters, hundreds of them, each one the signature of a collision with a fragment too small to have ever appeared in any tracking catalogue. The panels had been in orbit for years. Every one of those impacts was an untracked fragment striking a piece of hardware at orbital velocity. None of them caused the loss of the panels, but the lesson they represented was precise. The tracked population is not the only population, and the untracked population is not theoretical. It leaves physical marks on the hardware it encounters. ESA's 2025 report contains a statement that deserves to be read carefully. In the low Earth orbit range of around 550 kilometers altitude, the report says, there is now the same order of magnitude of debris objects posing a threat as there are active satellites. The same order of magnitude. The machines doing useful work and the fragments of machines that are no longer doing anything except posing a collision risk are now numerically comparable at the altitude where the largest commercial constellations operate. The ESA introduced a health index for the orbital environment in 2025 to make this situation easier for the public and policymakers to understand. The index, by the agency's own assessment, is trending in the wrong direction. If current behaviour continues, the report states, the risk level passes beyond the point of sustainability. Those last 6 words are not the language of a preliminary concern. They are the language of an institution that tracks this environment professionally, applies rigorous models to project its future trajectory, and has concluded that the trajectory is unsatisfactory. The question that the Starlink 34343 event brings into focus is not whether there is a problem. The problem is documented in detail by the agencies best positioned to assess it. The question is whether the individual events accumulating in the debris catalogue are symptoms of a process that has its own internal logic and momentum, a logic that was described with mathematical precision by a NASA scientist in 1978, in a paper that the space community spent decades treating as a theoretical curiosity before the data began making it impossible to set aside. Part 4. On January 30th, 2026, at 6 hours, 9 minutes and 3 seconds UTC, something changed in Graveyard Orbit. A short time-lapse produced by Orbital Tracking Networks documented what happened. A Russian satellite, catalogued as Luch Olymp with the tracking designation 40258, began to break apart in the high-altitude region above geostationary orbit, the band of space conventionally designated as the responsible disposal location for satellites that have reached the end of their operational lives. The fragmentation was observed by multiple independent tracking systems. The imagery made its way quickly into the small community of professionals who monitor the orbital environment for a living, and then, much more slowly and much more quietly, into the broader public awareness. Luch Olymp had a complicated operational history. During its active life, it had attracted considerable attention from Western space agencies and military analysts who accused it of performing unusual proximity operations, maneuvering close to Western satellites in ways that suggested surveillance or interference activities. The United States government had publicly characterized it as an inspector satellite, a term that in the language of orbital operations carries implications well beyond simple observation. But whatever its role during its operational period, by the time it fragmented in January 2026, it had been retired to Graveyard Orbit, which is where the story should have ended, and where, by the conventional logic of satellite disposal, the risk should have been contained. Jonathan McDowell, one of the most cited and most careful independent analysts of orbital events, told Space.com that the fragmentation of Luch Olymp may have been caused by an external debris impact. He noted that internal energy sources such as fuel tanks and batteries should have been vented when the satellite was retired, a process called passivation that is specifically designed to eliminate the risk of energetic internal failure after a satellite is decommissioned. While a failure to properly passivate the spacecraft could not be ruled out, McDowell said, a possible debris impact could suggest that the space debris environment in geostationary orbit and in the graveyard orbit above it is worse than previously believed. Worse than previously believed. That phrase carries considerable weight when it comes from someone with McDowell's track record of measured evidence-based analysis, because the graveyard orbit scenario changes the character of the orbital debris problem in a specific way that the discussion of low Earth orbit congestion sometimes obscures. Low Earth orbit, the region from roughly 200 to 2,000 kilometers altitude, is crowded, and the crowding is accelerating because of the massive commercial satellite constellations being deployed there. But LEO has one natural defense mechanism. At the lower end of that range, atmospheric drag acts as a gradual cleanup system. Debris doesn't persist forever. It slows, drops to lower altitudes, and eventually re-enters the atmosphere. The timescales vary enormously depending on altitude and solar activity, from weeks at 400 kilometers to years or even decades at 600 or 700 kilometers. But the mechanism exists. There is a process by which material leaves the low Earth orbit environment without human intervention. Geostationary orbit, approximately 35,786 kilometers above the equator, has no such mechanism. At that altitude, atmospheric drag is essentially zero. An object placed there stays there indefinitely unless actively removed. Graveyard orbit, the band above geostationary, operates on the same principle. Objects parked there do not come down. They drift, perturbed slowly by the gravitational influence of the Moon and the Sun and the non-uniform mass distribution of the Earth itself, tracing gradual changes in their orbits over decades and centuries. But they stay up. The geostationary belt itself is a uniquely valuable and uniquely finite resource. There are only so many positions in geostationary orbit from which a satellite can serve a given region of the Earth's surface, and those positions must be coordinated internationally to avoid interference between adjacent satellites. The belt is crowded with active satellites providing television broadcasts, weather monitoring, military communications, and emergency services across the entire inhabited surface of the planet. A debris field introduced into that environment by a fragmentation event does not dissipate. It evolves slowly under gravitational influences, spreads along orbital paths, and becomes a permanent feature of that altitude regime. If Leuciolymp was struck by a debris fragment in graveyard orbit, that means the debris environment in the high-altitude region has become dense enough to generate impacts against objects that were placed there specifically to stay out of the way. It means the disposal orbit is not as clear as the disposal logic assumed, and it means that the satellites currently retired to graveyard orbit, dozens of them from operators around the world, are sitting in an environment that may be more hazardous than when the graveyard orbit convention was established, when the population of high-altitude objects was a fraction of what it is today. The timing of this event relative to the Starlink failures below it creates a picture that is uncomfortable to contemplate in its entirety. In a window of approximately 3.5 months, beginning in December 2025 and running through March 2026, 3 documented fragmentation events occurred in Earth orbit. One at 418 kilometers, one in graveyard orbit above 36,000 kilometers, one at 560 kilometers, 3 different altitude regimes, 3 different operators or object types, 2 different apparent failure mechanisms. The low Earth orbit events involved internal failures of satellites still within their potential operational life. The high-altitude event involved a retired satellite that may have been struck by something. The professional community that tracks these events does not draw dramatic conclusions from individual clusters of events. The orbital environment is complex, the datasets are large, and the history of the field includes periods of elevated fragmentation activity, followed by relative quiet. Caution is warranted. But the pattern of the first quarter of 2026, laid alongside the trajectory described in the ESA's 2025 report and the tracking data from Leo Labs and other commercial monitoring networks, sits in a specific category of evidence. It is not proof of a cascade. It is not a definitive signal that the threshold Kessler identified has been crossed, but it is consistent with what you would expect to see in an environment that is moving toward that threshold in the specific altitude bands where the consequences matter most, and understanding what Kessler actually said and what the threshold he described actually means in physical terms requires going back to 1978 and a paper that the space community initially received as a careful projection, and that the data of the following 5 decades has been steadily transforming into something closer to a warning that arrived ahead of its time. Part 5. In June of 1978, a researcher named Donald Kessler published a paper in the Journal of Geophysical Research. Kessler worked in NASA's Environmental Effects Office at Johnson Space Center in Houston, and he co-authored the paper with a colleague named Burton Corpellet. The paper's title was precise and technical: Collision Frequency of Artificial Satellites, the Creation of a Debris Belt. It was not the kind of title that generates public attention. It was the kind of title that gets read carefully by the small number of specialists working in the area of orbital mechanics and space environment modeling. What Kessler had done was apply to the population of artificial satellites orbiting Earth a mathematical framework that had been developed to study collisions in the asteroid belt. The asteroid belt, the ring of rocky material between Mars and Jupiter, is governed by dynamics that have been worked out over billions of years. Objects in the belt collide. Collisions produce fragments. Fragments collide with other objects. The process is self-sustaining because the density of material is high enough that collisions happen faster than any natural dispersal mechanism can remove the resulting fragments. Kessler recognized that the growing population of satellites and rocket bodies in low Earth orbit was subject to the same underlying physics. The objects were different, the timescale was different, the density threshold was different, but the equations governing the cascade were the same. What the paper showed, in careful and well-documented mathematical terms, was that the density of objects in low Earth orbit would not need to reach anything close to asteroid belt densities before the collision dynamics became self-sustaining. The threshold was much lower than that, because the gravitational environment of low Earth orbit concentrates objects in a much smaller volume of space than the asteroid belt, and because the relative velocities of orbital objects are much higher than the typical collision velocities in the belt, meaning each collision produces more fragments with higher energies than a comparable asteroid belt collision would. The combination of relatively high density in a relatively small volume, high collision velocities, and the persistence of debris at altitudes where atmospheric drag is insufficient to provide rapid natural removal added up to a prediction that was straightforward and concerning. Given sufficient time and sufficient growth in the orbital population, a point would be reached at which the debris environment would begin generating more debris through collisions faster than any natural mechanism could remove it. Beyond that point, the environment would grow more hazardous over time, even without any additional human launches. The cascade would feed itself. The scenario was named after Kessler. The Kessler syndrome, the Kessler effect, collisional cascading, ablation cascade. The terminology varies by source but refers to the same underlying phenomenon, a runaway debris generation process in low Earth orbit that, once truly underway, cannot be reversed by natural means on any timescale relevant to human civilization. Kessler's original paper was received as an important theoretical contribution to the field of orbital mechanics. It was cited, studied, incorporated into models, and used as a basis for the debris mitigation guidelines that space agencies began developing in the 1980s and 1990s. The 25-year rule, which requires satellite operators to deorbit their hardware within 25 years of end of mission, was developed partly in response to the framework Kessler established. But for much of the following 2 decades, the Kessler syndrome remained primarily theoretical in public discourse. The populations involved were small enough that the cascade felt like a distant risk, something to plan for rather than something to respond to. That perception began to change in 2007. In January of that year, China conducted a test of its anti-satellite weapon system by destroying its own defunct weather satellite, the Fengyun 1C, in orbit at approximately 865 kilometers altitude. The test was successful in the military sense. The missile struck its target, the satellite was destroyed, and in the process, the test generated more than 3,400 trackable fragments and an estimated 40,000 pieces larger than 1 centimeter, all of them distributed in orbits clustered around 865 kilometers. At that altitude, atmospheric drag is negligible. The fragments will remain in orbit for decades, some for centuries, and each one represents a collision hazard to every other object that passes through that altitude range. Earth observation satellites, scientific research satellites, and weather monitoring satellites all operate in orbits that cross through the debris field created by that single test. Then, in February 2009, something happened that had never happened before in the history of the space age. 2 satellites, one active and one defunct, collided. The operational satellite was Iridium 33, part of the Iridium satellite phone network. The defunct satellite was Cosmos 2251, a Russian military communications satellite that had been dead since 1995 but had never been deorbited. The collision occurred at an altitude of approximately 790 kilometers, at a relative velocity of roughly 26,000 miles per hour. The 2 satellites were destroyed almost instantly, and the collision produced approximately 2,300 additional trackable fragments. Those fragments joined the debris field created by the 2007 Chinese anti-satellite test in orbits that will persist for decades. Together, those 2 events increased the trackable debris population by approximately 70%. The 2009 Iridium Cosmos collision is still regarded by many orbital debris specialists as the clearest early real-world manifestation of the Kessler dynamic. Not because one collision was the beginning of a cascade, but because it demonstrated that the density threshold Kessler had described was not a distant theoretical concern. The conditions for it to occur had been met. It had happened. By 2009, Kessler himself wrote that in his assessment, modelling results indicated the debris environment had already become unstable, meaning that efforts to achieve a growth-free small debris environment by eliminating past debris sources would likely fail because fragments from future collisions would accumulate faster than atmospheric drag could remove them. He was retired from NASA by that point. He was still watching, and what he was watching was a population of objects in low Earth orbit that, in the specific altitude bands where the density was highest, had already crossed the threshold he had described 30 years earlier. The 2025 ESA Space Environment Report puts the current state of this threshold question in terms that are careful but unambiguous. Even without any additional launches, the report states, the number of space debris would keep growing because fragmentation events add new debris objects faster than debris can naturally re-enter the atmosphere. The report identifies this condition in specific altitude bands. not uniformly across all of low Earth orbit, but concentrated in the shells where the density of active satellites is highest. The 500 to 600 kilometer altitude range, where the Starlink constellation and dozens of other planned commercial constellations operate, is identified explicitly as a region of concern, and the ESA's own health index for the orbital environment, introduced in 2025 to provide a single accessible metric for the state of the problem, shows the index trending in the wrong direction. The Kessler syndrome is not a hypothetical event on a distant timeline. It is a physical process with a specific mathematical structure, and the data from the agencies most qualified to assess it suggests that process is underway in the orbital shells that matter most to the infrastructure human civilization has built in space. The question that remains genuinely open, the question that keeps honest scientists from speaking in the definitive language of established fact, rather than the careful language of well-supported concern, is not whether the process is occurring, it is how fast it is proceeding, and whether the window for meaningful intervention is still open or has already begun to close. Part 6. In the first 6 months of 2025, SpaceX's Starlink satellites performed 144,404 collision avoidance maneuvers. Sit with that number for a moment. Not 144,404 total across the constellation's entire operational history. Not 144,404 in a year, in 6 months. That works out to a collision warning arriving somewhere in the Starlink constellation every couple of minutes, around the clock, every day, for half a year. And that rate was 3 times higher than the rate during the previous 6-month period. The number comes from IEEE Spectrum, which published a detailed analysis of the orbital debris situation in late 2025. The figure represents every instance in which a Starlink satellite received a conjunction warning, an automated alert indicating that another tracked object was predicted to pass within a defined safety distance, and then executed a propulsive maneuver to adjust its orbit and reduce the probability of collision. Each one of those maneuvers required the satellite's propulsion system to fire. Each firing consumed propellant. Each gram of propellant consumed in an avoidance maneuver is a gram of propellant that cannot be used to maintain the satellite's operational orbit, to extend its mission life, or to execute the controlled deorbit burn that is supposed to happen at the end of the satellite's operational period. This is where the physics of the debris problem and the economics of the satellite industry intersect in a way that the headline numbers about debris counts do not fully convey. The concern about uncontrolled satellites becoming debris is not simply about the hardware that fails catastrophically, the batteries that explode and the propulsion systems that vent. It is also about the much larger population of satellites that run out of propellant before completing their planned controlled deorbit, not because of a design failure, but because the propellant budget was consumed by hundreds or thousands of collision avoidance maneuvers during the satellite's operational life. A satellite that exhausts its fuel 6 months before its planned deorbit date becomes an uncontrolled object at its operational altitude. It does not deorbit, it drifts, and at 550 kilometers, drifting means persisting as a collision hazard for years. The ESA's 2025 Space Environment Report provides a metric that captures this dynamic in a single stark data point. In the altitude band around 550 kilometers, the report states, there is now the same order of magnitude of debris objects posing a threat as there are active satellites. Roughly equal numbers of operational satellites and debris fragments sharing the same orbital shell, with the debris population growing and the frequency of collision warnings therefore increasing, and the propellant budgets being consumed at rates that were not accounted for in the original mission designs, because the debris environment has evolved faster than the mission planners projected. The situation inside the ISS provides a different kind of illustration of the same trend. The International Space Station has performed 29 collision avoidance maneuvers since 1999, according to NASA officials. 3 of those maneuvers occurred in 2020 alone. The frequency has continued to increase in the years since. In November of 2024, the station performed 2 avoidance maneuvers within a 6-day period. Each maneuver requires the station's thrusters, or the thrusters of a docked spacecraft, to fire, adjusting the station's orbit to move it out of the path of an incoming fragment. The station is large, massive, and not particularly maneuverable. Each avoidance maneuver is a significant operational event requiring advanced planning and crew notification. And the station is not just a research facility. It is also, in the context of the debris problem, a large and complex target. Its surface area means it presents a significant cross-section to incoming debris. It cannot be made smaller, it cannot be made faster, it can only be moved, and moving it costs fuel and crew attention and operational complexity that is increasing year over year. There are also events that do not rise to the level of formal avoidance maneuvers, but that represent the daily reality of operating spacecraft in the current orbital environment. Satellites in highly congested orbits routinely receive conjunction warnings for objects that are too small to track precisely, meaning the probability estimates associated with those warnings carry significant uncertainty. Operators must make decisions about whether to maneuver based on incomplete information. Maneuvering costs propellant. Not maneuvering carries risk. Neither option is free. And the frequency of these decisions has been increasing consistently as the debris population grows and the density in the most congested altitude bands approaches, and in some cases reaches the thresholds that Kessler's mathematics identified as the preconditions for self-sustaining cascade. To understand what 144,404 maneuvers means at a more visceral level, consider a single satellite operator running a constellation of a few hundred spacecraft. Each satellite in that constellation is receiving conjunction warnings and executing maneuvers on a regular basis. The propellant budget for each satellite was calculated before launch based on the debris environment that existed at the time of the mission design. That environment has since evolved. The maneuver frequency is higher than projected. The propellant is being consumed faster than planned. The decision about when to deorbit each satellite, a decision that affects how long the satellite contributes to the constellation's service and how many customers it can support before being replaced, is being made in a context where the fuel budget is tighter than anticipated because the environment is more active than the mission designers assumed it would be. This is not a theoretical future problem. It is a present operational reality being managed by every major satellite operator in the congested altitude bands right now. The 144,404 figure is a snapshot of a process that was already accelerating at the time it was measured, and the Starlink 34,343 event adds a layer of complexity to that picture that the propellant budget calculations were also not designed to account for. A fragmentation event in the constellation's primary operational shell at 550 kilometers does not simply add fragments to the debris catalogue. It changes the conjunction warning frequency for every other satellite in that shell. Every operator in the neighborhood of 550 kilometers is now maneuvering more, consuming more propellant, shortening more mission lives, and increasing the risk that more satellites will run out of fuel before completing their planned deorbits. The cascade works not only through direct collisions, but through the secondary effects of an environment in which every event increases the operational cost of every other operator in the same altitude band. Part 7. The scenario Kessler described has a structure that makes it genuinely difficult to reverse once it begins operating in earnest. This is worth understanding precisely, because the temptation when discussing complex long-term environmental problems is to assume that intervention is always possible if it is timely enough, that the appropriate combination of technology, policy and investment can always pull a situation back from a threshold before the threshold becomes permanent. In most environmental problems, that assumption is approximately correct. The self-healing capacity of natural systems provides a buffer that buys time for corrective action. In the orbital debris problem, that assumption is incorrect in a specific and important way. The cascade, once it reaches a critical density in a given orbital shell, does not require any additional human activity to continue. Every collision produces fragments. Fragments produce more collisions. The rate of debris generation exceeds the rate of natural removal. The environment becomes progressively more hazardous, independent of whether any additional satellites are launched. This is the physical characteristic that makes the Kessler syndrome categorically different from most other environmental challenges. It is not a problem that stops getting worse when the activity creating it stops. It is a problem that continues getting worse on its own momentum, fed by the existing population of objects in orbit and the collision dynamics they generate among themselves. The sequence of events in a true cascade would unfold in stages, and describing those stages is useful, not because the cascade is imminent or inevitable in the form that science fiction envisions, but because understanding the mechanism makes it possible to understand why the intermediate warning signs matter, and why the language used by agencies like ESA in their annual reports is as serious as it is despite the careful and measured tone in which it is delivered. The first stage is exactly what the current environment looks like. Conjunction warning frequency increases, avoidance maneuver rates rise, propellant budgets are consumed faster than planned. Some satellites exhaust their fuel before completing planned deorbits and become uncontrolled objects at their operational altitudes. The conjunction warning frequency increases further, because there are now more uncontrolled objects in the shell. More avoidance maneuvers are required. More propellant is consumed. The feedback loop is already operating, if slowly and not yet catastrophically, in the most congested altitude bands. The second stage is more acute. Collision probability in the most congested shells reaches a level at which the fragmentation rate from actual collisions begins to be significant rather than occasional. Events like the 2009 Iridium-Cosmos collision, which had been without precedent in the history of the space age, begin occurring with greater frequency because the density of tracked and untracked objects in those shells has increased to the point where the probability of an uncontrolled conjunction, a close approach that no avoidance maneuver can prevent because the object generating the warning is too small to track, or because the operator lacks the propellant to respond, becomes material rather than negligible. Each such collision produces thousands of new fragments. The conjunction warning frequency increases again, the propellant consumption rate increases again, the feedback loop accelerates. The third stage is the one that the KESIM model, a stochastic simulation tool used by orbital debris researchers, projects as the endpoint of business-as-usual scenarios, exponential debris growth in specific orbital shells. Not linear growth, not a steady increase that can be outpaced by improved technology or compliance with deorbit guidelines. Exponential growth, in which each generation of debris generates a larger next generation, and the rate of increase itself increases until certain altitude bands become effectively unusable for any operational purpose. What disappears first, and this is the question that tends to focus the attention of people who had been regarding the debris problem as an abstraction, is not something exotic or peripheral. What disappears first is the functionality that the orbital environment currently provides, and that the global economy and global security architecture depend on, more completely than most people realize, because those dependencies are largely invisible when the systems are working normally. GPS fails first. Not instantly, not everywhere at once, but progressively, as the constellation of satellites maintaining the positioning system is degraded by damage, and as the replacement satellites cannot safely reach operational altitude through the debris field above the launch trajectory. The navigation you use to find a restaurant becomes unreliable. The timing signals that synchronize financial transactions across the global banking system become degraded. The precision agriculture systems that have increased crop yields across the developed world lose their accuracy. The systems that guide container ships through busy ports and aircraft through crowded airspace degrade. Each of these systems has backup modes. The backup modes are less precise, less reliable, and less comprehensive in coverage. The degradation is not a cliff edge, it is a slope. But it moves in one direction. Weather forecasting degrades next. The geostationary weather satellites that provide the continuous global coverage on which meteorological agencies base their models have finite design lives and require periodic replacement. If the orbital environment becomes hazardous enough that launching replacement satellites carries unacceptable risk, the weather modeling system begins running on progressively older and less comprehensive data. Hurricane forecasting becomes less accurate. Severe weather warnings become less reliable. Agricultural planning based on seasonal forecasts becomes less precise. Again, the degradation is gradual. Again, it moves in one direction. Communication satellite capacity degrades. This is most consequential not for the connected populations that have terrestrial fiber and cellular alternatives, but for the hundreds of millions of people in the developing world, in rural regions of every continent, in the maritime shipping lanes and remote industrial operations that depend on satellite connectivity as their primary or only telecommunications link. The global internet is not uniformly served by ground-based infrastructure. The portions of it that are served by satellite are the portions most vulnerable to a deteriorating orbital environment, and they are the portions least able to absorb the economic consequences of a degraded or interrupted service. Military satellite constellations which underpin the strategic posture of every major power and provide the intelligence, surveillance, and early warning capabilities on which national security decisions are based, become targets in this environment, not because anyone necessarily fires on them, but because the debris density makes it impossible to distinguish an intentional attack from a debris impact, increasing the risk of miscalculation at precisely the moments when clarity and confidence in intelligence assets matter most. None of this happens in an afternoon. The timescale for the cascade scenario that orbital debris specialists describe is measured in decades for the early stages and centuries for the full development of the worst-case outcome. The reason it matters now, in 2026, in the context of Starlink 34,343 and the cluster of events surrounding it, is not that the catastrophic endpoint is imminent. It is that the early stages, the stages that are reversible with sufficient political will and technological investment, are already visible in the data. The window for effective intervention is finite, and the window is open now in a way that it will not be indefinitely. Part 8. The end state of a fully developed Kessler syndrome across the most critical orbital bands is not an explosion visible from the ground. It is a silence. A particular kind of silence, incremental and cumulative, settling over systems that most of the people depending on them have never needed to think about because those systems have always worked, quietly and reliably, from orbital altitudes that most people will never visit and cannot directly observe. Understanding what that silence would feel like requires understanding how completely the global civilization that has developed since the beginning of the space age in 1957 has woven itself around the products of orbital activity. This is not a recent development, and it is not limited to the smartphone applications that use GPS positioning or the streaming services delivered via satellite. It runs through the foundations of the global economy and the security architecture that has maintained, imperfectly and unevenly but genuinely, a world in which catastrophic interstate war has been rarer than at any point in human history before the development of the surveillance and communications capabilities that satellites provide. Start with timing. The global financial system does not run on money alone, it runs on time. The synchronization of financial transactions across different time zones, different institutions and different national systems depends on atomic clock signals broadcast by GPS satellites, signals accurate to billionths of a second, the ability of banking networks to reconcile transactions, the ability of telecommunications networks to coordinate handoffs between towers and satellites, the ability of electrical power grids to synchronize generators across hundreds of miles of transmission infrastructure. All of these capabilities depend on timing signals derived from satellite-based atomic clocks. A degradation in GPS availability is not just a navigation inconvenience, it is a destabilization of the timing infrastructure on which the global economy runs. The extent to which this dependency is invisible in normal conditions is exactly proportional to the disruption that its interruption would cause. Move from timing to weather. The global weather forecasting system is an international collaboration of extraordinary complexity and demonstrated value. The models that predict tomorrow's weather, that track hurricanes and typhoons as they develop over warm ocean water, that tell airline dispatchers which routes to avoid and which atmospheric rivers will bring rainfall to drought-stressed agricultural regions, all of these models are fed continuously by observations from a network of geostationary and polar orbiting weather satellites that provide coverage of the entire Earth's surface and atmosphere at intervals of minutes. The accuracy of those forecasts, which has improved dramatically over the past 3 decades, correlates directly with the quality and continuity of satellite observation. A study by the European Centre for Medium-Range Weather Forecasts found that without satellite data, forecast skill degrades to roughly that of the 1970s within a few days of losing satellite observations. The 1970s forecasting accuracy meant that hurricanes that now tracked from their formation over the open Atlantic, with projections accurate to within tens of miles 5 days in advance, were then appearing on radar only hours before landfall. The difference in life safety is not marginal. Move from weather to agriculture. The Green Revolution that has sustained the growth of the global population from 3 billion in 1960 to 8 billion today was built on improved seed varieties, fertilizers, and irrigation. The green revolution of the 21st century, the one that is sustaining yields in the face of climate variability and water scarcity, is built on precision agriculture. GPS-guided tractors that apply seeds and fertilizer with centimetre-level precision, wasting nothing and maximising yield per acre. Satellite imagery that allows farmers to monitor crop health across thousands of acres and identify areas of stress before they become areas of loss. soil moisture sensors linked to satellite weather data that optimize irrigation timing to minimize water use. These systems are not optional extras in the agricultural economics of the developed world. They are the economic foundation of profitable commercial farming at the scale required to feed the current global population. Move from agriculture to maritime and aviation. The global shipping system, which carries approximately 90% of international trade by volume, depends on GPS navigation, satellite weather routing, and satellite communication for the management of a fleet of tens of thousands of container ships, bulk carriers, and tankers. The aviation system, which carries more than 4 billion passengers annually in normal years, depends on GPS approach and landing systems at airports worldwide, satellite weather data for flight routing, and satellite communication for oceanic flights where ground-based radar coverage does not exist. The specific system that handles communication and navigation for flights over the Pacific and Atlantic Oceans, regions that cover more than half the Earth's surface and that are transited by thousands of flights daily, has no complete terrestrial backup. If the satellite communications layer degraded significantly over an extended period, oceanic flight operations would need to revert to systems that have not been the primary mode of operation since before most currently active pilots trained. The transition would be managed, it would not be seamless. Move finally from infrastructure to security. The military satellite systems operated by the major powers, particularly the United States, provide capabilities that have fundamentally altered the character of warfare and international security. Real-time overhead imagery that allows military commanders to track the movements of adversary forces with precision that was not possible from ground-based intelligence before the satellite era. Communication systems that allow command and control over forces deployed globally. Early warning satellites that detect ballistic missile launches within seconds of the rocket's first stage ignition, providing the decision time that makes a rational response to a nuclear threat possible rather than impossible. The loss or degradation of these capabilities would not simply make military operations more difficult. It would change the strategic calculus of every nuclear-armed state, in a world where the stability of nuclear deterrence depends on the confidence each side has in its ability to observe what the other side is doing. None of this is speculative extrapolation about distant scenarios. Every one of these dependencies exists today, in the current world, operating on infrastructure that occupies the same orbital altitude bands, where the ESA's 2025 report identifies debris density trending toward unsustainable levels. The cascading scenario does not begin with a dramatic event visible from the ground. It begins with a gradual, almost invisible degradation in the reliability and longevity of the systems that provide these capabilities, as the cost of operating in a more congested and more hazardous orbital environment increases, and the rate of satellite loss to debris impacts climbs from occasional to frequent to unmanageable. The silence that the Kessler syndrome eventually produces, if it is allowed to develop fully, is not the silence of an empty sky. The satellites are still up there, the debris is still up there. The silence is the silence of systems that no longer work, that cannot be repaired because new hardware cannot safely reach orbit, that cannot be replaced because the orbital altitude they occupied has become too hazardous to operate in. It is the silence of services disappearing so gradually that by the time their absence is undeniable, the window for preventing it has long since closed. And understanding that window, understanding both what it represents and how much of it remains open, requires understanding what the industry and the agencies responsible for this environment are actually doing right now. Part 9. On January 1st, 2026, 2 weeks after the first Starlink fragmentation event, Michael Nichols, SpaceX's Vice President of Starlink Engineering, published an announcement on the social media platform X that has since attracted considerable attention in the orbital debris community. SpaceX, Nichols announced, would begin lowering approximately 4,400 satellites from their current operational altitude of 550 kilometers to a new operational altitude of 480 kilometers over the course of 2026. The announcement was notable not only for its substance but for the reasoning Nichols provided publicly to explain it. The physics rationale he offered was straightforward. At 550 kilometers during a period of reduced solar activity, an uncontrolled satellite, one that has lost propulsion capability or communication and can no longer execute a planned deorbit burn, can persist in orbit for more than 4 years before atmospheric drag naturally brings it down. 4 years of an uncontrolled object in the constellation's primary operational shell contributing to the conjunction warning frequency, consuming the attention and propellant of every other satellite in the neighbourhood, potentially colliding with something and generating a debris field. At 480 kilometres, the same satellite in the same solar minimum conditions would persist for a few months rather than a few years. Nichols described this as an 80% reduction in what he called ballistic decay time, the interval during which a dead satellite remains a hazard in its operational altitude before atmospheric drag removes it naturally. The physics is real. The improvement in debris residence time is genuine, and the move is consistent with a pattern of responsible behaviour that SpaceX has, in fairness, demonstrated more consistently than many other operators in the commercial space industry. The company's overall compliance rate with end-of-life deorbit guidelines exceeds 90%, substantially better than the industry average, and the decision to lower the constellation's operational altitude rather than simply accepting the longer debris residence time during solar minimum reflects an awareness of the system-level consequences of individual satellite operations that not all operators in the industry share. But the altitude-lowering plan has complications that are worth examining honestly, because this is one of those situations where the right move and the complete solution are different things, and treating them as equivalent would obscure the scale of what remains unaddressed. The first complication is the transition itself. Moving 4,400 satellites from 550 kilometers to 480 kilometers requires each satellite to execute a series of deorbit burns over an extended period, gradually lowering its orbit in stages until it reaches the new target altitude. During this transition, each satellite passes through the altitude bands between 550 and 480 kilometers, which are also occupied by debris, by other active satellites from the Starlink constellation and from other operators, and by the fragments from events like the Starlink 34343 breakup. A constellation executing 4,400 simultaneous altitude transitions is an unprecedented operational undertaking, and it occurs in an environment where the conjunction warning frequency is already running at levels that triggered thousands of avoidance maneuvers per day in 2025. The second complication is concentration. Compressing the constellation from a broader altitude range into a narrower shell at 480 kilometers increases the local density of active satellites at that altitude. Higher local density means higher conjunction warning frequency, which means more avoidance maneuvers per satellite per year, which means more propellant consumption, which means a higher proportion of satellites exhausting their propellant before completing planned deorbits. The improvement in ballistic decay time, the primary benefit of the lower altitude, is real, but it does not fully offset the operational costs imposed by operating at higher local density in the new shell. The third complication is the 3,532 V2 mini-optimized satellites that have already been identified as a potential concern. Lowering their altitude from 550 to 480 kilometers reduces the residence time of any fragments they might generate if they fail, which is good. But it does not address the question of whether those satellites have a higher than normal failure rate, what the root cause of the December and March failures was, and whether the design flaw, if there is one, affects the entire V2 mini-optimized population, or only a subset of it. SpaceX has stated it is working to determine the root cause. The answer to that question will determine whether the 3,532 satellites remaining in orbit represent a background risk of occasional failures similar to the historical average for commercial satellite constellations, or whether they represent an elevated risk that will generate additional fragmentation events before the root cause is identified and corrected. There are other responses in development beyond SpaceX's own altitude adjustment. The most ambitious active debris removal effort currently underway is a mission called ClearSpace One, a collaboration between the European Space Agency and a Swiss company called ClearSpace. The mission design is elegant in concept and formidably challenging in execution. A purpose-built spacecraft equipped with robotic arms is launched into orbit, navigates to a specific target object, a piece of hardware left over from a previous ESA rocket launch, and grapples it. The capture spacecraft then performs a deorbit burn, driving both itself and the captured debris into a trajectory that ends in atmospheric re-entry, burning up both objects harmlessly over the ocean. The first mission targets a single payload adapter, a relatively small object orbiting in a well-characterized orbit that has been drifting for years. The mission contract is valued at €86 million for one object. The number is not a criticism of ClearSpace or of the ESA. Active debris removal is genuinely difficult. The targets are tumbling, they have no docking interfaces, they cannot be commanded to hold still or to cooperate with the approaching spacecraft. Grappling a tumbling object at orbital velocity without creating additional debris in the process requires precision that has never been demonstrated operationally. ClearSpace is attempting something that has never been done, and the engineering challenge justifies the mission cost. But the scale problem is stark. ESA's own modelling suggests that stabilising the debris population in the most critical orbital shells would require the active removal of approximately 5 to 10 of the largest and most hazardous objects in those shells every year, sustained indefinitely. At current technology costs, that represents an annual investment of $500 million to $1 billion per year, with no obvious revenue model, no commercial customer paying for the service, and no international governance framework that would assign the financial responsibility for that investment to the parties whose orbital activities have contributed most to the problem the investment is addressing. The gap between what is being done and what the models say would be required to stabilise the environment is the most important and least discussed aspect of the orbital debris situation. SpaceX lowering 4,400 satellites is a meaningful step in the right direction, taken by one company in a commercial constellation. The global debris environment includes uncontrolled objects from dozens of countries, from rocket bodies launched over 60 years of the space age, from anti-satellite weapons tests, from the accumulated consequence of every mission that has ever operated in low Earth orbit and not fully cleaned up after itself. Addressing that legacy, on the timescale required to prevent the cascade dynamics from becoming irreversible in the most critical altitude bands, requires a response that matches the scale and the collective character of the problem, and the international governance framework that would make that response possible does not yet exist in anything close to the form it would need to take. Part 10. The most ambitious attempt to clean up the orbital environment currently in any stage of operational planning is a mission called ClearSpace One, and understanding both what it represents and what it does not represent is essential to any honest assessment of where humanity stands in its relationship to the problem it has created in low Earth orbit. ClearSpace is a Swiss startup founded in 2018, emerging from a project at the Swiss Federal Institute of Technology in Lausanne, with a mission defined by a problem that most startup founders would not have chosen if their primary objective was a straightforward path to revenue. The company's entire business case is built around the premise that removing objects from orbit is a service that someone needs to pay for, and that the combination of regulatory pressure, insurance costs, and institutional recognition of the sustainability problem will eventually create a market for that service, large enough to support a commercially viable business. The ESA's ClearSpace One mission, contracted to the company as its anchor customer and validation mission, is designed to demonstrate that active debris removal is operationally feasible at a scale sufficient to build upon. The target is a piece of hardware called a Vesper payload adapter, the upper section of a rocket that was used to launch an ESA satellite in 2013, and that has been orbiting since then at an altitude of approximately 660 kilometers. The Vesper adapter is a particularly instructive target choice because it represents a category of debris that accounts for a substantial portion of the mass of large objects in problematic orbits, rocket bodies, and their associated hardware. These objects are not small. The Vesper adapter has a mass of approximately 112 kilograms. It is roughly spherical in shape, which makes it somewhat more tractable for grappling than the irregular geometries of some other debris objects, and it is orbiting in a well-characterized, stable orbit with a known trajectory, meaning the navigation challenge of the rendezvous is manageable rather than extraordinary. The actual capture operation is the part of the mission that has no operational precedent. In the controlled environment of a laboratory, grappling an object with a robotic arm is a challenge that has been solved many times over in many different configurations. In the orbital environment, the same operation involves an object that has been tumbling in microgravity for over a decade, rotating on multiple axes at rates that can vary and that are difficult to predict precisely from ground-based observation alone. The ClearSpace spacecraft needs to approach the Vesper adapter, match its tumbling motion closely enough to safely contact it, without inducing additional rotation or generating debris from the contact itself, apply its robotic arms to capture the adapter, arrest the combined systems tumbling through thruster firings, and then execute the deorbit burn that ends the mission. Each stage of that sequence has failure modes that would leave the ClearSpace spacecraft itself as debris in the same orbital environment, which is a failure mode the mission design goes to considerable lengths to avoid. ClearSpace completed Phase 2 of its preparatory work in 2025, including rigorous testing of its robotic capture system in ground-based facilities designed to simulate the microgravity and tumbling dynamics of the target. The testing results were sufficient to proceed to the mission's next phase, but the mission has also navigated some of the complications that arise when the operational environment is not fully under the mission designer's control. In 2023, the Vesper adapter was itself struck by a piece of debris, a fragment too small to track that left it in a slightly different orbital configuration than when it was originally designated as the mission target. The irony of a debris removal mission target being hit by debris before the removal mission could begin is the kind of detail that would seem implausible in fiction, and that the orbital environment produces with perfect indifference to the dramatic inconvenience it creates. The mission cost, €86 million for the removal of a single object, defines one boundary of the problem's economic scale. The Aerospace Corporation, one of the United States' leading non-profit organizations focused on space system analysis, has modeled the debris environment and the costs associated with different levels of debris removal activity. Their analysis is consistent with the ESA's own modeling. Stabilizing the debris population in the most critical orbital shells requires removing approximately 5 to 10 large objects per year indefinitely. The total mass of the 10 most hazardous individual objects in low Earth orbit runs into the dozens of metric tons. The debris removal capacity that exists or is being developed as of 2026 is a fraction of what the models indicate is necessary. Astroscale, a Japanese commercial space company, has been pursuing a complementary approach through a project called COSMIC, a collaboration with the UK Space Agency. Their technology uses magnetic capture systems, and they completed an in-orbit demonstration of magnetic docking technology with their ELSA-D mission, which successfully demonstrated the ability to approach and dock with a simulated debris object equipped with a compatible magnetic interface. The limitation of this approach is the interface requirement. It works for satellites designed to be captured, not for the legacy debris objects that represent the greatest hazard. The broader commercial debris removal sector is in a state of early development that is genuinely hopeful in some respects, and genuinely inadequate in others when measured against the scale and urgency of the problem. The technology is being developed. The regulatory framework that would give debris removal operators permission to interact with objects owned by other nations, which is the central legal challenge because virtually every large debris object in orbit is technically the property of the state that launched it, is not resolved. The business model that would allow debris removal companies to generate the revenue needed to sustain operations at the scale the models require does not yet clearly exist. And the international governance mechanism that would coordinate the identification and prioritization of the highest risk objects across national boundaries and hold operators responsible for the long-term consequences of their orbital activities is still largely aspirational rather than operational. The ESA has introduced its own zero debris approach, a commitment to halt new debris generation in Earth and lunar orbits from all future ESA missions, programs and activities by 2030. The commitment is genuine and the goal is meaningful, but ESA represents one agency among many, and the agencies and nations most responsible for the current debris environment include actors whose relationship to international norms of responsible behavior in space has been demonstrably complicated by other geopolitical considerations. China's 2007 anti-satellite test, which created more than 3,400 trackable fragments in a single event, occurred after years of international discussion about the growing debris problem. Russia's 2021 anti-satellite test, which created over 1,500 debris fragments and forced emergency procedures aboard the International Space Station, occurred after those conversations had become more urgent and more public. The problem is not a lack of awareness. The problem is a lack of enforcement mechanisms, a lack of shared liability frameworks, and a lack of the political will to subordinate national commercial and strategic interest to the collective management of a resource, the usability of the orbital environment, that every state and every commercial operator depends on, and that no single state or operator has sufficient incentive acting alone to protect adequately. This is the classic structure of a commons dilemma, and the history of commons dilemmas teaches that they resolve in one of two ways. through collective governance that aligns individual incentives with collective outcomes, or through the degradation of the common resource to a point where it no longer supports the activities that depended on it. The orbital environment is a commons. The history of how humanity manages its commons is mixed. The outcome of this particular commons dilemma is not yet determined. Part 11. It is important to be precise about what the evidence does and does not show, because the orbital debris situation sits at a point where honest accounting is more useful and more genuinely alarming than either dismissiveness or catastrophism. The Kessler syndrome in its fully developed science fiction form has not occurred. The ISS is operational, GPS is functioning, global weather satellites are transmitting, communications constellations are providing service. The sky above you is not, right now, a debris field so dense that it cannot be safely navigated. And the events of the first quarter of 2026, the Starlink 34,343 fragmentation, the Lutulent breakup, the accumulating constellation of operational pressures, while genuinely concerning in the context of the long-term trajectory, do not represent an imminent civilizational threat of the kind that would justify emergency public alarm. What they do represent is something that deserves careful attention, precisely because of how it differs from an imminent threat. They represent the visible symptoms of a degradation process that is already underway, that has measurable momentum, that the agencies most qualified to assess it have described in their most recent official reports as trending toward the boundary of sustainability in specific orbital bands, and that will become irreversible at some point that is not decades away if current trajectories continue. The distinction between not imminent and not urgent is the distinction that tends to get lost in public discussion of this issue, and losing it is how collectively manageable problems become individually inescapable ones. The data that supports the concern is not speculative. It comes from primary sources with no incentive to exaggerate. The ESA Space Environment Report 2025, produced by the agency's Space Debris Office, using data collected through the end of 2024, and are published for the explicit purpose of providing transparent, evidence-based assessment of the orbital environment's condition, states in its summary that debris levels have increased 50% in the last 5 years in low orbit. It states that even without any additional launches, the number of space debris would keep growing because fragmentation events add new debris objects faster than debris can naturally re-enter the atmosphere in the most congested orbital shells. It introduces a health index for the orbital environment that, by the agency's own assessment, trends toward unsustainability if current behavior continues. These are not the conclusions of environmental advocates or policy campaigners seeking to generate momentum for a cause. They are the conclusions of institutional scientists doing the specific job of monitoring this environment for the global space community. The LEO Labs tracking data, which provides the most detailed commercially available picture of the orbital environment in real time, is consistent with the ESA's institutional assessment. The frequency of conjunction warnings, the rate of avoidance maneuvers, the number of fragmentation events generating new catalogued objects, all trending in the same direction. Jonathan McDowell, the most frequently cited independent authority on satellite tracking and orbital events, has described the current situation in terms that are careful and measured in the way that people with real expertise and real reputations to protect are careful and measured, but that also consistently convey genuine concern about the trajectory of the debris environment. The scientific community's honest position on whether the Kessler syndrome has already begun in certain orbital bands is not uniform denial. In a review of the Literature for Aerospace America, a journalist found that scientists with relevant expertise do not agree that the syndrome has definitively begun, but do agree that the concept is sound, that the space community needs to act differently than it has been acting, and that in some specific altitude ranges the dynamics Kessler described are already operating. That is not the same as saying the catastrophe has already started and nothing can be done. It is not the same as saying the concern is overblown and the system is self-regulating. It is the honest position. Something is happening. It is consistent with the predicted early stages of a concerning process, and the window for meaningful intervention, while still open, is not indefinitely open. The specific questions that remain genuinely uncertain are exactly the questions that honest science holds open while the data accumulates. Has the cascade threshold been crossed in any specific orbital shell? The ESA suggests the answer may already be yes in some bands, while noting that the models are simplified and the actual dynamics involve more variables than any current model fully captures. Is the V2 mini-optimized satellite failure pattern a systematic design flaw or a statistical cluster of random failures? Unknown, pending SpaceX's root cause analysis. Will the Louche Olympe fragmentation prove to have been caused by a debris impact, which would indicate that the graveyard orbit environment is worse than previously characterized? Unknown, pending further analysis. How many of the 3,532 V2 mini-optimized satellites currently in orbit will experience similar failures before the root cause is identified and addressed? Unknown. These unknowns are not a reason to dismiss the concern. They are a reason to take it seriously enough to resolve the questions, because the questions are answerable, and the answers matter for the decisions about investment, regulation, and international coordination that need to be made in the near term if the long-term trajectory is going to change. The window that is still open, the reason the situation is not already hopeless, is a combination of physical and institutional factors that give the problem genuine tractability if the collective will to address it materializes before the physical dynamics become dominant. The physical factor is that lower orbital altitudes benefit from atmospheric drag in a way that higher altitudes do not. The most populated and most vulnerable orbital shells are in the range where, during periods of elevated solar activity, natural removal mechanisms operate on timescales of years to decades rather than centuries to millennia. This means that improved compliance with end-of-life deorbit guidelines, combined with targeted active debris removal of the largest legacy objects, could in principle reduce the debris population in the most critical shells over time. It is not a self-healing system that requires only that the degradation stop. It requires active management. But active management, properly resourced and internationally coordinated, is physically capable of producing an improvement. The institutional factor is that the awareness of the problem, the technical understanding of its dynamics, and the political and commercial motivation to address it have all increased substantially in the past decade. The commercial space industry has a direct financial stake in the usability of the orbital environment. Insurance markets are beginning to price debris risk in ways that create financial incentives for operators to comply with deorbit guidelines that were previously treated as aspirational targets. Regulatory bodies in major spacefaring nations are tightening the requirements for debris mitigation in operating licenses. ESA has committed to its zero debris approach for all future missions. The conversation has shifted from academic awareness to institutional urgency in ways that were not visible a decade ago. Whether those developments will translate into action at the speed and scale the models indicate is necessary is the question that belongs to the future rather than the past. The evidence from the first quarter of 2026, culminating in the Starlink 34,343 fragmentation and the cluster of events around it, suggests that the future in question is closer than it has ever been. The problem is visible, the data is available, the physics is understood, the window is open. What happens next depends on choices that have not yet been made by institutions and governments and commercial operators who have not yet committed to making them. That is not a comfortable place to be, but it is not a place where the outcome is already determined. Not yet. Part 12. There is a particular quality to looking at the night sky after you understand what is actually up there. Not the stars, not the planets, not the moon, the other things. The things that move steadily and silently across the background of fixed stars, visible for a few minutes after sunset or before sunrise, when the geometry is right, and the sunlight catches their solar panels or their metallic skin and reflects it back to you in a brief, moving point of light. There are more than 10,000 Starlink satellites in orbit right now. On a clear evening, in the right conditions, you can watch several of them cross the sky in the time it takes to drink a cup of coffee. Each one is a piece of infrastructure. Each one is a repeater tower for an internet service that someone, somewhere in the world, is using as their primary connection to everything outside the physical radius of their daily life. Each one is also, eventually, an object that will need to come down, and the question of how and when and in what condition it comes down is a question whose answer shapes the orbital environment that every other satellite in the same altitude band has to operate in. The fragments that Starlink 34,343 scattered into the volume of space around it on March 29th, 2026 are still up there. They will be up there for months, possibly years, depending on the solar activity cycle and the specific orbital parameters of each individual fragment. Most of them are too small to track individually. They exist in the debris catalogue as a statistical enhancement to the known population in the altitude band, captured in the aggregate measurements that Leo Labs and the military tracking networks use to characterise the debris environment, rather than as individually identified and monitored objects. They cannot be avoided because they cannot be found precisely enough to generate actionable conjunction warnings. They drift through the orbital shell, carried by the same dynamics that govern every other object at that altitude, occasionally passing close enough to another satellite to generate a warning if they are large enough to be tracked, more often passing close without anyone knowing it happened, or at least without anyone knowing it happened until the next constellation-wide audit of satellite telemetry reveals unexplained anomalies in a handful of spacecraft that happened to be in the wrong place at the right time. This is the daily reality of operating a satellite in 2026. It is not the reality that was described in the mission planning documents when the first generation of these constellations was being designed and permitted and launched. The debris environment has evolved faster than the mission designs anticipated. The operational cost of managing a satellite in the current environment is higher than the original business cases assumed. The margins that looked comfortable when the constellations were designed look less comfortable now, and the question of how many of the planned second generation and third generation constellation expansions can be commercially sustained in an environment where each satellite is performing avoidance maneuvers at 3 times the rate projected. Consuming propellant reserves that were sized for a cleaner environment is not a question that has a comfortable answer, and yet the services those constellations provide are genuinely valuable. The rural communities in the developing world that now have reliable internet access for the first time because of low Earth orbit, broadband satellites are not abstractions. They are real communities whose connection to the global information economy, to health resources and educational materials and market price data and emergency services exists because of satellites that were not there 10 years ago. The crisis response operations that use satellite imagery to direct relief supplies after earthquakes and floods and hurricanes in regions where ground-based infrastructure has been destroyed are not abstractions. They represent the real-world value of orbital capability applied to human welfare at its most fundamental level. The tension between the value the orbital environment provides and the risk that the pace of its use creates is not a tension that resolves cleanly in favour of either side. What resolves it, or fails to resolve it, is governance. The management of shared resources that are too valuable to abandon and too fragile to use without coordination. The history of such resources on Earth provides both cautionary examples and genuine success stories. The cautionary examples are well documented. The success stories are less often cited but equally real. The Montreal Protocol, the international agreement to phase out the production of chemicals that were depleting the stratospheric ozone layer, is the example that orbital debris specialists most often invoke when discussing what successful international governance of a shared atmospheric resource looks like. The ozone problem was diagnosed, the mechanism was understood, the solution was technically feasible, and the international community coordinated to implement it on a timescale that, while not without difficulty, prevented the worst projected outcomes from materializing. The ozone layer is recovering. The orbital debris problem is different in important ways. The ozone problem had a cleaner causal chain, specific chemicals produced by specific industries, causing measurable damage through a well-understood mechanism. The orbital debris problem involves hundreds of operators from dozens of nations, decades of accumulated legacy material, and a cascade mechanism whose threshold is uncertain enough to create genuine scientific disagreement about how urgent the response needs to be. But the structural similarity is real. A shared resource, a well-understood degradation mechanism, a technically tractable solution if the political will can be organised to implement it, a window that closes over time as the physical dynamics become more dominant. The window is open. This is the most important thing to carry from the events of March 2026 into whatever comes next. The window is open. The Starlink 34,343 fragmentation is not a signal that the cascade has begun and cannot be stopped. It is a signal that the environment is operating closer to the edge of manageability than the public discourse generally reflects, and that the distance between the current trajectory and the point where options begin closing deserves more serious attention than it receives in a news cycle that measured the story in days before moving on. The debris from Starlink 34,343 is still orbiting above your head as you listen to this. The 3,532 other satellites of the same model are still circling the planet every 96 minutes, and the root cause of the failure that ended their predecessor is still under investigation. The Russian satellite in graveyard orbit is still broken, its fragments drifting in the high-altitude band that was supposed to be the responsible disposal location. The 1.2 million fragments larger than 1 centimetre are still there, invisible to ground-based tracking, moving at 17,000 miles per hour through the same volume of space occupied by the infrastructure that provides GPS and weather forecasting and communications to 8 billion people. The cascade that Donald Kessler described in 1978 is not a future threat on a distant horizon. It is a physical process with a mathematical structure, and the data of the past decade describes a debris environment that is moving in the direction that process requires. Whether it moves far enough to become irreversible before humanity organizes an effective collective response to prevent it is not determined by the physics alone. The physics sets the constraints. The physics defines the thresholds. The physics describes the outcomes with mathematical precision, given specific inputs about debris generation rates, active removal rates, compliance with deorbit guidelines, and the collision dynamics of an environment with specific density characteristics. But the inputs are not fixed. They are choices. They are the accumulated consequence of decisions made by satellite operators about how to design and operate and deorbit their hardware, by governments about how to regulate the orbital environment and enforce the regulations they create, by international bodies about whether to develop the governance frameworks that would align individual incentives with collective outcomes, and by the public about whether this issue receives the sustained attention that would create the political conditions for those decisions to be made responsibly. The sky is not falling. That is not the message. The message is more demanding than that. The sky is something that we built into incrementally and without fully accounting for the cumulative consequences of each individual addition, and it is now telling us, in the specific language of fragmentation events and escalating avoidance maneuver rates and debris density measurements that trend in one direction, that the way we have been using it cannot continue indefinitely without consequences that would be very difficult to reverse. You live under that sky. The satellites circling above you right now provide services that your daily life depends on in ways that are mostly invisible precisely because those services are working. The question that the events of the first quarter of 2026 leave on the table, the question that the data in the ESA's annual reports and the LEO Labs tracking databases and the IEEE spectrum analyses of maneuver frequency and propellant consumption have been accumulating toward for years, is whether the moment when the invisibility becomes visibility, when the dependency becomes apparent because the service has degraded, arrives before or after the governance and technology required to prevent it are actually in place. That question does not have an answer yet. It belongs to the decisions that have not yet been made, by people who are not yet fully aware that the decisions need to be made, about a resource that will determine the shape of the century that is just beginning. The window is open. The question is whether we are paying attention while it still is. The weight of what we cannot see. There is a specific kind of vulnerability that comes from depending on something you cannot observe. It is different from the vulnerability that comes from depending on something fragile but visible, something you can watch and tend and repair when it shows the first signs of failure. The orbital environment is the defining example of the invisible dependency, a lattice of infrastructure woven through the space above the atmosphere, providing services that the economy and the security and the daily logistics of the modern world could not function without, and that virtually no one who benefits from those services can see, monitor, or intervene in when something begins to go wrong. This invisibility is not incidental to the debris problem. It is a central feature of why the problem has developed to its current extent, without generating the sustained public and political attention that a comparably scaled problem in a visible domain would have attracted long ago. If the debris were falling into rivers instead of orbiting silently above the atmosphere, the regulatory response would have been forceful and early. If the conjunction warnings were audible as street noise rather than silent telemetry exchanges between satellite computers and ground stations, the accumulating frequency of those warnings would have registered as a public concern long before it registered as a technical metric in a specialist community's annual report. But the orbital environment is silent and invisible to everyone who is not specifically instrumented to observe it. The people who are instrumented to observe it, the debris tracking networks, The Space Situational Awareness Services, the satellite operators monitoring their fleets through telemetry channels, have been documenting a trend that is now more than a decade old and accelerating. The documentation exists, the models are available, the ESA publishes its Space Environment Report annually and makes it freely accessible. The data is not hidden. The problem is not that the information is unavailable. The problem is that the information exists in a domain that the broader public has not been equipped to translate into the concrete terms that would make it feel as urgent as the numbers, properly understood, suggest it is. The 1.2 million fragments larger than 1 centimetre orbiting above you right now do not feel like a crisis because you cannot see them or hear them or find them affecting your daily experience in any way that is attributable to them. The GPS worked this morning. The weather forecast was issued. The internet connection was maintained. From the perspective of the ground-level user, the orbital environment is performing normally, delivering its services reliably, functioning as designed. The gap between that ground-level experience and what the debris tracking data shows is exactly the gap in which the debris problem has been developing, steadily and without the acute urgency that would attach to a problem whose consequences were immediate and personal, rather than gradual and systemic. Understanding the orbital environment requires a specific act of imagination that most of the discourse around this issue fails to facilitate adequately. It requires holding in mind simultaneously the invisible and the dependent, the hundreds of millions of fragments you cannot see, and the services they threaten that you cannot imagine living without. It requires extending the intuition that says if something that depends on X is at risk, then I am at risk, from the familiar domains where that intuition has been developed, to a domain that feels remote and technical and managed by specialists in ways that make personal engagement feel neither possible nor necessary. The specialists who manage it have been trying to communicate the urgency of the situation to the broader community for years. The language they use is careful because they are scientists and engineers whose professional culture values precision over rhetoric, and who are aware that overstating the immediacy of a risk damages credibility for future communications. But read carefully enough, the careful language says something unambiguous. The environment is degrading. The degradation is accelerating. The tools available to slow or reverse it are currently deployed at a fraction of the scale the models indicate is required, and the window during which those tools could be deployed at the necessary scale before the cascade dynamics in the most critical orbital shells become self-sustaining in a way that cannot be addressed by anything short of multi-generational efforts at orbital remediation is not indefinitely open. The events of March 2026 did not create this situation. Starlink 34343 is a data point in a trend that has been developing since before the first Starlink satellite was launched, and the trend exists independently of whether SpaceX had been operating in low Earth orbit at all. The Chinese anti-satellite test of 2007, the Iridium Cosmos collision of 2009, the Russian anti-satellite test of 2021, the dozens of rocket body explosions that have each contributed hundreds or thousands of new fragments to the debris catalogue, the cumulative consequence of 60 years of orbital activity in which the Commons was used as though it would absorb any load placed on it without consequence. All of that is the context in which the March 2026 events need to be understood. They are not the beginning of the problem. They are the problem, rendered visible in a specific and recent and therefore more accessible form. What March 2026 offers, if it is received correctly, is a moment of clarity about where the trajectory of the orbital environment is headed, and how much time remains to alter that trajectory before the alteration requires a level of effort that would dwarf anything currently being contemplated. The satellite that shattered on March 29th produced fragments that will persist in orbit for months, possibly years. The model that shattered it may have produced 3,500 potential future events of the same kind. The environment that surrounds both of them has been accumulating debris and complexity for 60 years and will continue to accumulate it faster than any current removal capacity can offset. These are the facts. They are documented. They are verifiable. They are not disputed in their broad outline by any serious voice in the community that studies this domain professionally. The question they leave behind, the question that outlasts the news cycle and the social media attention and the specialist commentary, and eventually even the memory of a specific satellite on a specific Sunday in March, is whether the civilization that built this infrastructure is capable of governing it with the seriousness and the coordination that its value and its fragility both require. Whether the invisible dependency can be acknowledged clearly enough to generate the political will to protect it. Whether the window stays open long enough for the answer to that question to be yes. The sky above you is not falling, but it is not static. It is not empty. It is not the background of a fixed and passive setting for the story of human activity happening below it. It is a managed commons in the early stages of a management failure, monitored by instruments and professionals who see the trend clearly, capable of being corrected if the resources and the governance are applied at the necessary scale, and trending toward a threshold that, once crossed in the specific altitude bands where the consequences are sharpest, will not uncross on any timescale that is meaningful to the civilization, depending on the infrastructure above it. The window is open. That is still the most accurate thing that can be said. And somewhere above you, orbiting once every 96 minutes, the fragments of a satellite that broke apart on a Sunday morning are still circling, silent and invisible, waiting for whatever comes next. The math that only moves one way, when orbital debris specialists say that the mathematics of the cascade only moves in one direction, they mean something specific, and it is worth understanding exactly what they mean. Because the precision of that claim is both its most alarming and its most clarifying feature. In most complex systems, interventions can produce improvements as well as degradations. You can add pollution to a river, and you can remove pollution from a river. You can overfish a fishery, and you can establish a moratorium that allows the population to recover. The reversibility of the damage is assumed unless there is specific evidence to the contrary, and that assumption of reversibility shapes the political economy of environmental management in ways that tend to make action easier to defer than it would be if the damage were understood to be permanent. The orbital debris cascade does not work this way in the altitude bands, where the debris density has already approached or exceeded the critical threshold that Kessler's mathematics identifies. In those bands, the accumulated debris is already generating new debris through collisions faster than atmospheric drag can remove it. Stopping all new launches tomorrow would not reduce the debris population. It would only slow the rate at which new material is being added at the top, while the existing population continues to generate new fragments at the bottom through the collision dynamics already in motion. The only intervention that can actually reduce the debris population in a given orbital shell is active debris removal, physically capturing and deorbiting the objects that are driving the collision frequency. And as the ClearSpace One mission illustrates, active debris removal at the scale required is not a technology that exists in operational form anywhere in the world today. The economic structure of the problem compounds the physical one. The orbital environment is a common pool resource in the precise economic sense defined by the Nobel Prize-winning economist Elinor Ostrom, a resource that is both non-excludable, meaning no individual user can be easily prevented from accessing it, and rivalrous, meaning one user's activity affects the resource available to others. Common pool resources are subject to a well-documented dynamic that Garrett Hardin called the tragedy of the commons in a famous 1968 paper in Science magazine. Each individual user of a common pool resource captures the full benefit of their use while distributing the costs of that use across all other users of the resource. The rational calculus for each individual user therefore favours overuse, because the personal benefit of any given use exceeds the personal share of the cost it imposes. The aggregate result of many individually rational decisions is collective overuse that degrades the resource for everyone. The orbital environment fits this structure precisely. Each satellite operator captures the full commercial benefit of their constellation while distributing the debris risk of their operations across every other operator in the same altitude band. The more operators there are, the more diffuse the cost distribution becomes, which further reduces the individual incentive to internalize the costs of responsible operation. The result is an environment in which individual compliance with debris mitigation guidelines is imperfect, in which the guidelines themselves are set at levels designed to be achievable rather than levels designed to be adequate, and in which the cumulative consequence of individually rational decisions by dozens of operators over 6 decades is a commons that is now being managed in the early stages of a crisis that no individual operator has sufficient incentive to prevent on their own. Ostrom's research on the governance of common pool resources identified the conditions under which communities of users can develop effective self-governance that prevents the tragedy. The conditions are specific. Clearly defined boundaries for the resource and its users, rules adapted to local conditions, collective decision-making processes, effective monitoring, graduated sanctions for rule violations, mechanisms for dispute resolution, and recognition by external authorities of the community's right to organise itself. The orbital environment meets almost none of these conditions in a form that is operationally effective. The boundaries are defined in principle by international space law but contested in practice. The rules vary by national jurisdiction and are set without adequate mechanism for international enforcement. The monitoring is improving but remains incomplete for the small objects that drive the collision dynamics. The sanctions for rule violations are essentially non-existent. The dispute resolution mechanisms are inadequate, and the recognition by external authorities, meaning the major spacefaring nations, of any effective international governance structure for the orbital environment is aspirational rather than operational. The gap between the governance structure the orbital environment has and the governance structure it requires is not simply a matter of political will, although political will is certainly part of it. It is also a matter of institutional design. The existing international framework for space, rooted in the 1967 Outer Space Treaty and its successors, was developed for a space age in which the primary actors were national governments operating a small number of large, expensive satellites for scientific and military purposes. The treaty's provisions reflect the concerns of that era, particularly the concern about national sovereignty and the risk of the militarization of space in ways that create specific complications for the management of the debris problem in the current era of commercial mega-constellations and hundreds of operators from dozens of countries launching thousands of satellites per year. The Outer Space Treaty establishes that states bear international responsibility for their national activities in space, including the activities of non-governmental entities operating under their jurisdiction. This provision, Article 6 of the treaty, was intended to ensure that states could not escape responsibility for their space activities by delegating them to private actors. In the context of the debris problem, it creates a framework in which states are responsible for the debris generated by their nationals and their registered spacecraft. But the mechanism for holding states accountable for that responsibility in practice does not exist in any operationally effective form. No state has been held liable for debris generated by its space activities. No international court or tribunal has jurisdiction over such claims that any major spacefaring nation would accept. The accountability mechanism is theoretical rather than operational. The satellites you depend on tonight, there is a specific and useful exercise in thinking about what orbital infrastructure actually means in daily life, not as a collection of technical capabilities described in the abstract, but as the invisible enabler of specific things that specific people do on a specific day. Today, the day you're listening to this. The weather forecast you checked this morning, whether you consulted it to decide what to wear or to plan an outdoor activity or simply out of habit, was produced by a modelling system fed continuously by observations from a constellation of weather satellites in geostationary and polar orbits. The geostationary satellites provide continuous coverage of large regions from fixed positions 35,000 kilometers above the equator. The polar orbiting satellites provide global coverage by crossing the entire planet twice daily, sampling the atmosphere at every latitude with instruments that measure temperature, humidity, wind speed, cloud cover, and dozens of other variables that the models use to project future states of the atmosphere. Without that continuous satellite observation, the forecast you checked would not exist in anything close to its current form. The delivery that arrived at your address was routed using logistics systems that depend on GPS positioning at every stage, from the warehouse management systems that track inventory, to the route optimization algorithms that assign delivery vehicles, to specific areas to the signature capture devices that create the confirmation record of the delivery. The GPS timing signals that enable the route optimization are provided by a constellation of approximately 30 satellites orbiting at roughly 20,200 kilometers altitude, maintained by the United States Air Force, with equivalent systems operated by Russia, Europe, and China. Every navigation system on every smartphone, every truck, every ship, every aircraft, every construction equipment system that uses GPS is continuously receiving signals from these satellites and using them to determine position and time with the precision that the current logistics economy requires. The financial transaction you made today, whether you used a credit card, a mobile payment system, or a bank transfer, was settled using timing signals derived in part from GPS satellite atomic clocks. The synchronization of financial networks across different institutions and different time zones requires a common timing reference accurate to within microseconds. The GPS satellite constellation provides that reference. Without it, financial networks would need to operate on alternative timing systems that are either less precise, less universal, or both. The transaction would still complete. The financial system would not collapse. But the precision and the speed and the global interoperability of the current system depend on satellite-derived timing in ways that most people who use financial services have no reason to know. The food you ate today was very likely grown using precision agriculture techniques that depend on satellite positioning. The tractor that planted or harvested the crop may have operated on autopilot guided by GPS, maintaining centimetre-level accuracy across field rows that would require a full-time human operator to navigate manually. The irrigation system may have been scheduled based on satellite weather data. The yield monitoring system that maps the field's productivity may have combined GPS positioning with sensor data to create the productivity maps that guide next season's input decisions. The efficiency gains from precision agriculture, the reduction in seed, fertilizer, and water use per unit of food produced are embedded in the economics of food production across the developed world in ways that would take years to substitute, even if the satellite positioning data disappeared gradually rather than abruptly. Each of these is a piece of the invisible architecture that satellite infrastructure provides. Each of it is at the other end of the chain of dependencies that begins with a satellite in low Earth orbit, maintaining its position and its function in an increasingly congested and increasingly hazardous environment. The Starlink 34,343 that shattered on March 29th was not carrying weather data or GPS timing signals. It was carrying internet traffic for broadband subscribers, but it was orbiting in the same altitude band as thousands of other satellites that collectively represent the new layer of the satellite economy, and the environment it broke apart in is the same environment that every other satellite in that band navigates daily at escalating operational cost. The connection between the debris on a Sunday morning and the forecast on your phone the following Wednesday is not direct. It is systemic. It is the connection between the condition of a commons and the reliability of the services that depend on it. And the condition of the commons, as documented by the agencies most qualified to assess it, is trending in the wrong direction at a rate that has been accelerating. What 60 years looks like from orbit, the space age began on October 4, 1957, when the Soviet Union launched Sputnik 1, a polished aluminum sphere roughly the size of a beach ball, into an elliptical orbit that carried it between 228 and 947 kilometers above Earth. Sputnik 1 broadcast a simple radio signal on 2 frequencies. It had no other instruments, no mission beyond demonstrating that orbital flight was possible. It remained in orbit for 3 months before atmospheric drag brought it down, and it burned up on re-entry on January 4, 1958. For 3 months, it was the only man-made object in Earth orbit. It was alone up there, a single point of light crossing the sky in 96 minutes, audible as a beep on shortwave radio to anyone with the right receiver, visible to the naked eye on a clear night as it passed overhead. Today, in the first quarter of 2026, approximately 11,800 active satellites share the orbital environment with tens of thousands of inactive objects and millions of fragments. The transition from 1 to 11,800 happened not suddenly but cumulatively. Through 68 years of individual launches, each one justifiable in isolation, each one contributing its increment of useful capability and its increment of debris risk to the commons. The first debris-generating event happened almost immediately. Vanguard 1, launched in March 1958, is still in orbit today, the oldest man-made object in space, its batteries long dead, its mission long concluded, a piece of hardware from the Eisenhower administration drifting silently in an orbit. That atmospheric drag will not clean up for another century or two. It is the first member of a population that now numbers in the millions when counting all fragments above 1 millimeter. The growth of that population was not linear. It accelerated with each decade as the pace of launches increased and as the events that generate large numbers of fragments occurred. The 2007 Chinese anti-satellite test added 3,400 trackable fragments in a single event. The 2009 Iridium Cosmos collision added 2,300 more. The 2021 Russian anti-satellite test added over 1,500. Each fragmentation event from exploding rocket bodies adds dozens to hundreds of fragments. The cumulative consequence of 60 years of this activity is the environment that Starlink 34,343 broke apart in on March 29, 2026, an environment that is incomparably more hazardous than the one Sputnik 1 occupied alone in 1957, and that is becoming more hazardous at an accelerating rate as the commercial mega-constellations add thousands of new objects to the most congested altitude bands each year. The scale of the transformation over 60 years of the space age is genuinely difficult to internalize at full scope. In 1957, there was one object in orbit. By 1970, there were approximately 1,000. By 1990, several thousand. By 2010, roughly 15,000 tracked objects, including debris. By 2020, the number had grown to approximately 27,000 tracked objects, as the commercial satellite boom accelerated. By 2025, it stood at approximately 40,000 tracked objects, of which about 11,000 were active satellites, and the remaining 29,000 were inactive objects, rocket bodies, and debris large enough to be individually tracked. And below the tracking threshold, the population of fragments larger than 1 centimetre has grown to 1.2 million by ESA's latest estimates. That trajectory from 1 to 40,000 tracked objects and 1.2 million untracked hazardous fragments in 68 years is not a background rate of stable growth. It is an accelerating curve, and the physical dynamics of the cascade mechanism, if they become fully operational in the most congested shells, would make that acceleration irreversible by the natural forces available to counteract it. The irony embedded in this trajectory is that the growth has been driven almost entirely by the development of genuinely valuable capabilities. Weather satellites that save lives, communication satellites that connect communities, Earth observation satellites that monitor climate, track deforestation, detect natural disasters, and support the management of natural resources, navigation satellites that enable the precision logistics of the modern economy, scientific satellites that have revealed the structure of the universe, mapped the surface of Mars, detected gravitational waves, and measured the expansion of the cosmos. Every one of these capabilities came at a cost to the commons, and the cost has been accumulating for 6 decades in a domain where most of the people benefiting from the capabilities have not been aware that a cost was being paid. The generation now entering positions of authority in governments and corporations and international institutions is the first generation for which the orbital environment has always been occupied and actively managed. The generation of the space age founders, the people who built the early satellites and established the initial norms of orbital operation, worked in a world where the debris problem was theoretical. The generation that followed them worked in a world where the problem was emerging but still manageable. The current generation works in a world where the trajectory of the problem, if it continues unchanged, leads to outcomes that would significantly constrain or eliminate the orbital infrastructure that the global economy and security architecture depend on. The decisions this generation makes, or fails to make, about debris mitigation compliance, active debris removal funding, international governance frameworks, and the commercial incentives that shape operator behaviour will determine which trajectory the orbital environment follows over the next half-century. The window is still open. The evidence supports that claim and demands that it not be overstated. The cascade has not become irreversible in the most critical altitude bands, not yet. Not by the assessment of the agencies monitoring those bands with the best available tools. The debris environment is degrading. The degradation is accelerating. The gap between the current response and the response the models indicate is necessary is significant. But the physical mechanisms